Welcome, guys. So previously that we already talked about cardinality. So this video we talk about a metric space. Okay, so given a set x, right, non-empty, and we can create a function from x to x, mapped to the real number which greater or equal to 0. It's called a metric. So basically satisfy the dpq given any 2 point pq in x greater or equal to 0 if p is not the same as q, dpp equals to 0, right? So and also so which it tell you that if they are not the same, they're greater than 0. If it's the same, it's 0. So it may basically also say that if it's the same, then 2 point must be the same. Okay, and should be symmetric, right? So this is the distance, and the third is that the triangulated equality. Right, for PQR belongs to X. Okay, this is called a distance function. Okay, so the standard example. The standard example is take X to be the n-dimensional Euclidean number, and given any 2 points, defined to be the standard distance. Right, so you can write as a vector. Yeah, so basically it's the standard one. Okay. Okay, so definition. So starting now, we can start in a simple topology in a metric space. So open bracket AB means that all the real numbers such that x, a, and b. Okay, and also close AB, close interval, x belongs to real number such that this. Okay. Okay, and let's talk about so-called open ball. Okay, so in n dimension, Rn dimension pick, I write BR x0s, so it means that the open ball with the radius along x0s. So this means that all the y such that y minus x0 less than r. Okay, about what is the distance? Yeah, so sometimes okay, so you can write as this. But sometimes I'm very lazy, so I will write absolute value. But when I write absolute value, I mean the specific d function. I mean the general d function. So yeah, so I mean you can write as this. Okay, so this is open ball. Okay, also define a thing called the convex. So convex is also an important idea. So basically, if I say the subset A belong subset A of X, it's called convex. So what do we mean by convex? Convex means any 2 points can connect it, right? So any 2 points, let's say x0 and y0, you draw a line, and all these lines fall into A. Okay, so mathematically, what it says that lambda x0s plus 1 minus lambda y0s for all lambda belongs to 0, 1. All these points, let's say call it P of lambda. So P of lambda must be inside A for all lambda. So this is a definition. So geometrically just means that you pick any 2 points, then this line must be this line must fall into a set. So you see these two, right? So this, if this is A, this is not convex, right? Because if you pick this point, then this line will not in A. Okay, so theorem exercise. So balls. So ball, right? Ball. So open ball, right? With BR x0s is convex. Okay, so this should be viewed as a stupid exercise. So check it by yourself. Okay. Okay, so many definition. So start from now, we talk about a lot of definition. Okay, so let's say A is called neighbors. So neighbors, there is a miss H. So neighbors means that the neighbor of P basically is a set of NRP. Yeah, basically I can write as BRP. Okay, so the neighbors of P means that basically just says the there's a radius r greater than 0, such that this p, so BRP contains this. So basically, when I say neighbor of p, how I'm saying is that I choose a particular r, which is sometimes I don't specify it, right? I call it BRP. So basically, this is p, and then there's a radius r, and these are called neighbors. Okay, so when I say neighbors, then you should think that I pick up some open ball. And the r is the radius, okay? And the b is called limit. So if p is called limit point, okay. So by the way, you take a matrix space X, okay, and take a subset E, okay. So if p is called limit point of E, if so, this is very important. So what is limit point? So basically, you have E, right? So limit point means that yeah. So some your intuitive this is P, right? So the limit point of E, if every neighborhood, so every neighbor, so that means you pick up any neighbor. Okay, so now I use NBHR to abbreviate neighbor. So every NBHR of P intersection with E will be non-empty. Okay, this is called the limit point. Okay, so very important things that this is not enough, right? Because if P belongs to E, right, then it become so this becomes trivial, right? Because P belongs to E. If P belongs to E, then any neighbor will intersect with E will be non-empty. Also, I want to, so there's a condition. The important condition is that every neighbor of P contain a point Q, which Q not the same as P, such that Q belongs to E. Okay, so I should write every neighbor of P contains a point Q, and Q do not belongs to P such that Q belongs to E. So this one should be the correct definition. So you see, however ball I choose, there's always some point which is not the same as P but intersect with E. This is called limit point. Okay. See. So if P belongs to E, and P is not limit point, so P is not a limit point. P is not a limit point of E, then P is called isolated. So this is just definition. So isolated means that suppose this is my E, right? And I pick up also E contains a point which just a point, right? So this point is not a limit point, right? Because there is a neighborhood, it doesn't intersect with E non-trivially, and also it belongs to E. So this is the isolated point. Okay, so D, if E is closed, so this is my closed definition. If E is closed, means that every limit point, every limit point of E belongs to E. Okay, so what I mean saying is that every limit point of this set E is just falls in E cell. So somehow like you can view if there's an open ball, right? And this open ball is not closed. The reason is that you can pick a boundary. This boundary you can take any neighborhood, and you see this is a limit point, right? But this point do not belongs to E itself because this is open. Okay, so open ball is not closed. Open ball is not closed. However, the closed ball are closed, right? So you can close it. Okay. Okay, E. So E, I will talk about interior. So interior is a little bit stupid. Okay, so if P is interior of E, P is interior point of E. So that means there is an open ball or neighborhood of there exists R greater than 0 such that the BRP falls into E. Okay, so basically, suppose you draw a circle, right? And any points inside the circle, right? You can pick up small ball, which this ball inside a circle is called the interior point. Okay, so F. So E is open. So what do you mean by open, right? Open means that every interior point, every point of E is interior point. Okay, so this means that so for example, this open ball, right? So open ball, any point of open ball, you can find a very small open ball, right? Which you need. right? So this is the example. So open ball is open. Well, it'll be stupid, right? Every point of E is interior point. Okay, so complement of E. So definition, the complement of E is very easy, right? Just call it E of C. Just all the points belongs to X, but the P do not belongs to E. Okay. H. E is perfect. So what is perfect set? So E is closed and also E is perfect. So E is perfect means it's closed and every point is a limit point. Okay, so we might talk about some theorem like the first category or second category of the basically there's a thing called this guy. So we may talk some special topic about the perfect set. Okay. Okay. Also, I is bounded. Okay. So also bounded. Bounded means that there is this m, right? Such greater than 0, such and point q. So you can find so basically you can find a q in x such that so every point belongs to E. You get dpq less than m. So ideal basically this set is compact because I can draw a large circle which cover it. Yeah, so basically compact the bounded, sorry, not compact. Bounded means that this guy is bounded by you can make a circle which cover it. So in the metric space means that you can find a point P, which you can find a point Q in X, right? Q in X, Q not necessary inside E, but you can outside E, and then you draw a large ball which can cover it. So basically, for every P belongs to E, your dpq should less than N. Okay, J. So E stands. So E stands in X. Basically, it means that every point of X is a limit point of E. Or E itself. Okay, so you can view E stands in X. Basically, this is X, and then there's a E, right? Which E is very, very close to X. So such that every point in X cannot be separated from E. Okay, so example can be viewed as we make rigorous proof, but the ideal is that Q, right? Your rational number is dense in R. So basically, you on real numbers, you pick any real numbers. There are two cases. Either it's rational or irrational, right? Rational means that in Q, irrational means not in Q, right? But I can always find a point which is very, very close to this point, but which is rational. Okay. Okay, so theorem. Neighborhood is a okay, so this theorem is trivial. Okay, so let's skip. Okay, so theorem says that if P is if P is a limit point, if P is a limit point of E, then every neighborhood, so every neighborhood, so NBHD, so every neighborhood is just the open ball or open set of points, right? Of P contains infinite many of E. Okay, so yeah, so let me remind you guys quickly that what is limit point, right? So limit point means that every neighborhood, right? Every neighborhood of P contains a point Q, and the Q is not the same as P. Okay, so yeah, so this means that okay, so let's draw some picture. So this is E, right? So you can either so however Q, right, however neighborhood you draw, which is small, can be arbitrarily small. However list you draw, there must exist some Q, which is Q not the same as P, such that Q belongs to E. Okay, so this is a definition, right? So we need to prove, try to prove it contains the infinite many of E. Okay, so proof. Suppose not. Okay, so suppose not. Let's suppose you only contains the finite point, right? So there exists the neighborhood of P. So N is a NBHD of P contain contains only finite point. So let's say Q1, Q1, Q2, up to let's say Qn. So it's a point. It's a point. So our points n intersection with E, right? So this is E. This is P, right? So I suppose there is you can only find there is a neighborhood such that it only contains the finite point. So some finite points. Okay, and all of them are now the same as P, such that n intersection E. And I take the minimum, right? So I can, since it's finite, so I can take the minimum of the P and the Qi. Okay. Okay. So obviously, right from here that you can okay. So right. So now you can find another number which is smaller than R. So let's say you find X, which is X and is R. And which you create a ball. So you create a ball with radius X, which X length S and R, and the original is this P point, right? So this point do not contain any point, right? I mean, it's the open ball. It's an open neighborhood, so it's open ball, so it's an open neighborhood contain at starting at P with the radius X, right? But X is less than this, right? So this guy is less than this guy is a subset of n, right? Because n is not open neighborhood, so itself must be open. Okay, so yeah, so this is a neighborhood of P, also in a less subset of n, right? But it did not contain the point of E, right? Because we choose X to be less than R. Okay, so which contradiction that this is the limit point. Right, the limit point means that the arbitrary neighborhood of P should contain at least some points which is inside E, but not the same as P. Okay. Okay, so theorem, which is corollary, so a finite set does not have, so finite set is not sorry, the finite set does not have limit point. Okay, so this is due to the previous reason, right? Because if you have finite set, then which points should be limit, right? Because the limit set at least should contain, you pick any neighborhood should contain infinite points. Okay, and also there's a simple lemma that I don't want to prove. I think it's trivial. So you can any set go E alpha, you union, and take the complement will be the intersection of each complement. Yeah, so this is somewhat like the De Morgan law. Yeah, so the proof should be trivial by your logic, right? Because a union means that it falls in one of them, complement means that it do not fall in one of them. So you just written a logic, you prove that this is true. Okay, so the proof is trivial. Yeah, so theorem. Yeah, so remember that I define a closed set means that every point is an interior point. I define a closed. Okay, sorry. I define an open set. So remember my definition is open means that all the interior points, all points are interior points. Okay, and I define closed to be set E is closed if all limit points of E belongs to E, right? There's another definition, closed, called that closed is the complement. If a set is closed, means that complement is open. So what we're going to prove is that a set is open if and only if E complement is closed. Yeah, so this is the usual definition, but in routine, we use the limit point idea to prove. Okay. Yeah, so hopefully, probably this is the first non-trivial one. Okay. Okay, so proof. Okay, so the first is suppose E the complement is closed. Closed one. Okay, so that means pick up X belongs to E. Right. So by definition, X belongs to E means that X do not belongs to this one, right? So since this is closed, right? So X will not be the limit point. Why? Because closed set contains all the limit points, right? So let me write the important word. X is not a limit point of EC, right? So it's not, right? So that means what? You can find the open ball, right? By previous result, so you can find the open ball. You can find it. you can find n, right, such that n contains x, right, and the n intersection, the complement is empty, right? If it's not, then it will be a limit point, right? So you can find n, which is the open neighborhood of x, which is open, and the n intersection with complement is empty, right? Okay, but this means what? N intersection the complement is empty. Should say it's the same as n fall inside E, right? The reason is that otherwise that you suppose you got some point which is inside N but outside E, which will be the E complement, right? So this sentence change to this sentence. So this means that you given any point X, you can find N which is N cover X and N really inside E. So E is open. Okay. Okay, another direction. So suppose suppose E is open. And then we want to show that, so we want to show EC is closed. Okay, and hopefully the proof is so so convert so you try to inverse this argument, right? Right, so E is open, right? So the X be a limit point of EC, right? So by definition, X is a limit point. So every neighborhood of X, right? So every neighborhood of X should intersect with EC. Intersect with this EC contains infinite point, right? Point. So which says that? See, which says what? So X is limit point of EC, right? And yeah, this is definition. But I mean, if X is a limit, let's see. Yeah, X is a limit point of E complement, right? So that means every neighborhood of X contains a point. Every neighborhood of X, right, contains a point of E complement. So X is not interior point of E. Okay. So from this we know that X is not an interior point. Interior point of E. Why? Because the reason is that if X is the interior point of E, then you should define something which is always fall inside E, right? Right, but the problem is that no, right? The problem is that whatever n you choose, intersection with E complement always contains infinite point. So there is a problem that X is, so from this sentence, you definitely can say that X is not the interior point of E. Okay, but if X is not okay, so the reason is that E is so okay, so X is not interior point of E, right? Also, since X is open, so what? So X belongs to E complement, right? Because E is open, so every point is an interior point. So if X is not interior point, then definitely X will becomes the complement of the E, right? By definition. So let me say again. So by definition, E is open means that every point is interior points. No, X not. So now X is not interior point. So X will be the complement, right? So every limit point become the every limit point of the complement E of C must be inside. So EC is closed by definition. So every point, limit points in itself means the closed set. Okay, so this is final results. Let me say very important. So it's open if and only if EC is closed. Okay, and yeah, okay. So there's still a lot we want to say about the open and closed set. Yeah, maybe let me see. Let me see what time is it. Okay. Okay, so let's maybe talk another. Okay, so let's maybe talk another theorem. Okay, so this theorem is very I should view it as an exercise, but maybe I prove some of it. Okay, so you take any open. So this is very important. I think. Hope you guys, you guys, this is the basic. So any collection. So any collection of open set. Let's say you take G alpha, right? And you get the whatever union is open. Okay, so this is really important. Okay, and the second is that you still take any open collection of open sets. Finite intersection is open. Okay, so finite intersection. So maybe alpha 1 to maybe n is open. So this is important that arbitrary union is open, but only finite intersection is open. Okay, so conversely, so not conversely, you can dualize, right? Because you take the complement, you take the complement itself, you take a complement. So the A translation is that any collection of closed set any collection of closed set G alpha, the intersection, so that is called F alpha, F means closed. So any intersection of closed set can be infinite, must be closed. And any collection of closed set and only finite union is closed. Okay, so let me just say using the words. So infinite union of open will be open. Finite union of open will be open. Okay, so you take a complement which tells you that infinite intersection. So also infinite finite intersection. I'm stupid. Okay, so infinite intersection of closed set give you closed. So this changes to finite union of closed means closed. Okay, so this is our code to prove our proof. Okay, so you take complement of these, right? You get the third, you take this, you get so only probably only non-trivial part are these two, right? Okay, so let's prove. So let's talk about how to prove that let's say the code X, and then we want to prove that this is open if every GI is open, right? But this is trivial, right? Because you can pick X. By definition, you can find a ball which is like called Rix, such that this BI ball which inside GI, right, for every I. So you can take a union, so you get right. So you can take so each ball, right, can force into BIX such which BRX which inside GI, right? And then you just take a union, so you get this. Right, so you just take a union. Yeah, sorry, this is union. Okay, so now for each X, right, you can the union of this unit ball. Okay, so you need to somehow like try to prove this guy. You need to somehow try to prove this guy is open, right? But you don't, right? The reason is that you can take whatever, right? You can take the BR1, BR1 X, right? So for each X, you can take the ball BR1 X, which is inside all this and all this. So this is the open neighborhood you can choose, right? So you already find open neighborhood which cover X, which inside all set. So this is open. Is open, right? So this is trivial, right? Because in each point you already have a ball which satisfies your results, so you can just take it. Okay. Okay, but how about intersection? How about intersection? So intersection should be trivial, right? But the problem is that the problem is that for each I, right? So for each I get some for each point X, I get some, let's say BRIX, which is also inside GI, right? But I want to prove the intersection. The problem is that if I take an intersection, it's not guaranteed that if I take an intersection, right? Let's say we take a zero from I to N. Okay, it's somehow like this X, right? I get R1, maybe R2. So R1 is inside, let's say G1, R2 is inside G2. Someone like or maybe yeah. So we need to care about intersection. Okay. Okay, but we can do this, right? We can take R to be the minimum of R1, R2 up to R, right? So we take a smallest radius. Okay, so hopefully you guys see the trick. Okay. Okay, so you can take R1 and also R2 and also R3. And then you take the minimum R, right? So your BR of X will inside this minimum R will inside all the intersection, right? Because this is all the ball, right? So definitely it needs GI I from 1 to n. Okay, so this is still open. But the problem is that so that's why we only need finite. So if you take it to be infinite, then there may be a case that your ball keeps shrinking. Right, finally your radius becomes 0. Right, so we only get a point. Okay, so counter example is that you take 1 minus n, 1 over n, and then you take n from 1 to infinity. You take the intersection, and this guy will be only get the points called 0, right? Because you get this. But so everything in this guy is open, right? Because this is open interval, is open ball, so this is open. But finally, the intersection is closed. Okay, so the finiteness is important. Okay, so maybe next time we talk about the closure and the compact. Okay, so next time, closure and compact set. Okay, and prove the terrible real. See you guys next videos. Bye bye.